Hello everyone, this is Spencer Snolling from Hydromantis, and I'm glad you've been able to join us for our monthly webinar series today. Today we're going to be talking about using the GPSX Optimizer tool and how you can use this advanced simulation tool to help with your designs, with your operational studies, and take advantage of the search routine that is built into it that can help you out. So my name is Spencer Snolling. I'm VP of Product Development here at Hydromantis, and I'm very happy to be speaking to you today from our new office. This is the first webinar that we've been broadcasting from our new place. We're located now at 407 King Street West. It's just about a 5-minute walk from where we used to be. If you happen to be in the area, we'd love for you to drop by. All of our contact information, our phone numbers and so on have not changed. It's really just our mailing address and our physical location. So the agenda for today's webinar is to start out with an introduction to numerical optimization and talk a little bit about how that works in GPSX, to talk about typical applications where you can use this tool, talk about and demonstrate how to set up an optimization in GPSX with different types of input and output parameters. And I'm going to be running 3 desktop demonstrations today that will illustrate different ways in which you can use the optimizer tool. And lastly, I'm going to wind up with some tips to help you make it all work as best it can, and also a few pitfalls that you will want to avoid. And as always, we'll be here to answer any questions that you have. As always, you can use the questions panel of your GoToWebinar dashboard. Open that up, type your questions in, and I'll just let those accumulate as I'm talking throughout the webinar. And when we get to the end, usually about 30 minutes or so, I'll take some time at the end of the webinar to answer those as best I can. Okay, so let's jump right in and talk a little bit about numerical optimization. The GPSX Optimizer tool is something that you can use with a completed model. So you've put a model together in GPSX, you've entered in all the information, you've run simulations, you're happy with the calibration and everything is fine. What you can then do is let GPSX take control of a couple of the parameters and do a search routine to find the best answer for a specific objective that you're looking at. So that's accessed through this button here, the one that's supposed to look like a simulation going through a bunch of data points, and that's up in the top toolbar. And the optimizer tool is only available if you have the GPSX Pro license. So that's what we used to call our advanced license. So if you're not sure what kind of license that you actually have, you can get a hold of us and we can sort that out for you. So optimization is a word that actually has a lot of different meanings. So what I'm going to be talking about it today, I'm talking about it in making something as good as possible in one particular aspect. So that often reflects itself when we're doing wastewater treatment in better effluent, lower effluent concentrations, or it may be a better operating cost, a lower operating cost, or better consistency. Maybe not the lowest parameters possible, but something that is giving you a reasonably consistent or sort of optimally consistent performance over a period of time when there's some dynamics coming through your plant. So it's up to you to decide how you want that to be. Modeling is really a key tool and a very handy tool to be able to carry out optimization studies in wastewater treatment plants, as I'm sure you know. They can provide a really cost-effective way to try out different plant designs, different operational strategies, see what works, see what doesn't work, and then kind of iterate through a bunch of different times to try and make things as good as they can be. So in that sense, you are doing optimization in that way, but you're doing it manually by hand, by making small changes to a number of the model inputs, maybe one at a time or two at a time, in order to sort of explore a region of performance, a region of behavior of your particular plant, and try to push it in the direction that you want it to go to achieve a specific objective there. Well, there are automated methods that can be used to do the same thing, and that's what the GPSX Optimizer tool is. It can perform a search for you and find the absolute most optimal set of parameters for a given objective function that you have defined. Now, these mathematical automated methods have a number of advantages, not the least of which is that it can do it in a very sort of wide range. It can really explore a large range of behaviors to go to a wide range of different parameter values and really get you what you would call the best answer. There's local improvements, and there's sort of a globally best answer, and there's different methodologies to go through to try and find all those things. And then probably the number one reason that it's very handy is because it's automated and it's fast. It performs simulation after simulation after simulation while automatically making changes to the parameters and moving in a direction which will make the simulation better. So there are a number of typical applications which we've seen our clients using them and which we've used for ourselves. All of those optimizations require a very specific objective. And usually when you're trying to do an optimization, you're trying to minimize or maximize something. So minimize an effluent ammonia concentration or maximize digester gas production or something like that. It also is possible that you may set it up to seek a specific value. So not the largest or smallest value, but I actually want to have an effluent total phosphorus of 0.5. Like I want to get that number exactly. So that can be a very handy target for it to shoot for. So when I'm talking about these optimizations today and what we can do with the GPSX optimizer, it really boils down to two different things. We can do what we call process optimization. That's this minimizing or maximizing of some particular output of the model. And so that's often taking this, and this is a screenshot from the demonstration I'm about to show you, where we'll start out with an effluent total nitrogen up here, and then as GPSX is going through the process of finding a better set of operational parameters, it will find that it can get the total nitrogen down lower, down to down here. So we're minimizing effluent total nitrogen in this case. The second one that you can use it for is not actually minimizing or maximizing something, but fitting to a number of data points. So in this particular case, this is sort of useful for calibrating your model, which you'll feed in some dynamic data like what I'm showing on the screen here. And then you'll let the GPSX optimizer move some parameters around so that it can get the simulated, the solid line, to match up as closely with the dots, with the actual measurement data there as possible. So I'm going to show you an example of that as well. So optimization can be used easily to determine the optimal sizing for tanks or for zones within tanks. It can be used to optimize flow control options for wet weather events such as step feeding or bypassing. It can be used for optimal pump flow and blower rates for doing energy reduction. It really pretty much can be applied to any type of question that you can construct within GPSX. So you can give it any sets of parameters that you want as the input. You can specify any output as that thing that you're trying to minimize or maximize. It may not work out, but it's a completely open and free-form thing that you can do in GPSX. So the general approach when you're doing an optimization is to first of all define that objective function. So you're telling that you want to fit to a specific set of data points, or you want to specify a parameter or parameters and say I want you to minimize or maximize these things. Then you give control of some of the input parameters over to GPSX. So you specify which are the optimized parameters, the ones that you want it to be making the adjustments to. So this would be things like pump flow rates or tank sizes. And you specify what those are. You specify any boundary conditions on those optimized parameters. So you may not want it to go outside a certain range. Say you have a DO set point that you don't want it to go too high or too low. You can specify ranges. And then specify the termination criteria. In other words, how good is good enough? If you're going to allow it to sort of make changes as it wants to, it needs a way to end, and we have a number of good default settings for that particular thing. So once that is done, this numerical, I'm sorry, I got back onto the same slide there. The optimizer will then perform basically simulations over and over again while adjusting those inputs and assessing the outputs. So it'll make a run, it'll take a look at that target variable that you're trying to minimize, and then it will say, is this better than the last run that I had or the last few runs that I had? And if it is, then it keeps going in that direction and it moves those parameters a little bit farther. I'll show you an illustration of how that works here shortly. So for the example, let's say we were trying to minimize total effluent nitrogen here, effluent total nitrogen. So that is a specification of that objective function. We then select parameters that we are going to allow it to adjust. So let's say, for example, in a plug flow tank, we are going to allow it to adjust the dissolved oxygen set points. It can control where the air is going to go. We can set some boundary conditions, well, in this case, no negative DO set points. So we're going to allow it to go all the way down to 0, and then the termination criteria is basically stop when the changes between one guess and the next set of guesses become very small. And it uses a simplex method to find that best set of parameters to seek that objective. Now, the simplex method is a fairly well-known optimization method, and we use it in the wastewater industry because it is something that allows us to do the optimization through evaluating successive versions of the model under different inputs. It doesn't require us to do any sort of analytical analysis of the derivatives or anything. We can basically just take a set of parameters, evaluate the model at that set, then evaluate it again with a different set and so on, and compare those to each other to find out which way is the way that makes things better. It's very good for problems that are nonlinear or have a number of discontinuities, and that's really good for these ASM type wastewater models that we have. They have not discontinuities, but they certainly have very sharp changes in the sensitivity of the model when you're getting to a point where you're either sort of right on the edge of nitrifying, for example. The name comes from the simplex, which is a geometrical figure consisting in n dimensions of n plus 1 points. Now, I know that sounds kind of theoretical, but what it is really it takes the number of parameters, n is the number of parameters that you have, and then n plus 1 is the number of guesses that it keeps track of at any one time. And it sort of flips back and forth between different sets of guesses, and it keeps track of the best 3 that it was working from at any one time. So the easiest way for me to explain that is actually through this animation that we've put together here. So let's take a look at that total effluent nitrogen minimization that I've been mentioning. And in this case, we're going to set up our optimization problem as find the best set of these parameters, which is the anoxic fraction here. What fraction of this overall activated sludge tank is going to be, what fraction of it is going to be anoxic? And the internal mixed liquor recycle rate, which here comes from the end of the aerated zone back to the beginning into the anoxic zone. And find the best set of those parameters that will minimize effluent total nitrogen here at the end of the plant. So what it does is we have 2 parameters. So, and I'm plotting this here, one versus the other. So we have an initial guess where we're going to start here. This is the anoxic fraction, 30%, and this is the internal mixed liquor recycle rate here, which is 500 meters cubed per day. So as I mentioned, we take n plus 1 points. So we take a second guess and then a third guess. And we move them around a little bit so that they're spread out from each other. And this forms a triangle. This is our simplex. This is our initial 3 guesses that we use to figure out which way is going to make a better guess and which way is going to improve the total nitrogen. So in the effluent, we evaluate what the total nitrogen in the effluent is like for each one of these 3 guesses. And they're going to be different from each other, and one of them is going to be the worst guess. Now, because we're doing a minimization, the worst guess is the highest effluent total nitrogen. And so let's, for argument's sake, say we're going to start with that first guess being, that worst guess being the first one over here. Then what the optimizer does is it reflects that through the other 2 points to get to a new guess. And then it immediately checks to see if I go even farther, does that make it even better? And then it double checks to back up and see, is there a spot over here where maybe that was a better guess? So whatever it comes up with is its best guess. It stops, it looks at those 3 new points, that n plus 1 number of points, and then it draws the new simplex. And then it evaluates those 3 points again and figures out which one was the worst one, and then it reflects it through. And it does that over and over and over again, and it allows it to make changes each time it wants to do a simulation by getting rid of the worst guess and creating a new better guess. And we always know that that reflected point will be better than at least one of the points that it's being reflected through. So it's a way to make sure that it is always going, so to speak, downhill towards the correct answer. So let's imagine that we have the surface here. This is the effluent total nitrogen at these particular coordinates of anoxic fraction and internal mixed liquor recycle rate. And we're trying to find that minimum point that is over here. So we'll start with our initial guesses and our initial simplex, and then we reflect through, and that got better. So we'll reflect through again and again. And basically, as it keeps running and replacing points, eventually gets to a point where that guess was maybe not actually the best guess. If we went, oh, one too far, this guess over here is actually worse than this one. So what it does is it backs up, it contracts, it then continues on its process of finding new places and contracting and flipping and reflecting through each point until it finally gets to a point which it knows to be the best job that it can do. It can no longer minimize effluent and that total nitrogen anymore. So that's what it looks like in a theoretical sense. But now let's actually get over to seeing what it looks like when we do it in GPSX. So first of all, I should mention if you've used the optimizer in GPSX in the past, in version 6.5, which came out around Christmas time, we've completely changed the way that you set up an optimization. We now have a new menu, a step-by-step menu that takes you through all of the required steps that are there to set that up. So all of the options with respect to selecting your variables and importing your data and so on are now done through this menu. So the first thing you do is you click on the optimizer button on that top toolbar, and that brings up this window. And there's some steps that it's going to go through here that are shown on the left-hand side. So the first thing you have to do is check off what is your target variable? What is the variable that you want to minimize or maximize? Then you have to specify all of the things that you want the GPSX to have control over. Those are the optimized variables, the ones that GPSX is going to adjust every time it runs a simulation. And then there are a number of other settings that you have to do as well. You have to specify whether it's minimize, maximize, or fit to data, whether it's a time series fit. And I'm just going to leave it and talk about time series for today. We'll have to come back and do the probabilistic and other things at some other time in the future. And also the objective function itself. You can define different types of objective functions. But for the most part, everything I'm talking about today will work with the relative sum of squares, no problem. And then once that's done, it will build the model, flip it over for you to simulation mode, and you'll note that it will put up all of the optimized parameters that you have specified, and it will also turn on optimize mode down here in the corner. And then you're ready to go. You can hit start and it will run. So that's what I'm going to do. Right now, I'm going to pop over here to GPSX and show you a couple of examples of what that looks like. So first of all, as I mentioned, you click on this button up here at the top, this optimize button, and you'll get a window that pops up. Sorry, it came up on my other monitor there. This is what it looks like. And as I mentioned, it takes you through the process here. So I've already gone through and set this up, but I'll show you what it looks like when you do that. First of all, you have to specify the target variables. And what we're going to be doing in this particular example is essentially the version that I just was showing you earlier, which is to take a look at adjusting internal mixed liquor recycle and the anoxic fraction of the tank in order to minimize total nitrogen. So in this case, target variables is the effluent total nitrogen off the backside of the clarifier here. So I go to clarifier, I go to that particular connection point, and as you probably know, total nitrogen is found in the composite variables menu, and it's under the more button here. Sometimes you have to dig way down to find what you're looking for. There it is, total nitrogen is checked off. So then I can go next, and then now I'm specifying the optimized variables, those things I want to be adjusted. And so that we mentioned that that was internal mixed liquor recycle rate, and that is found in the aeration menu here. So if I go to operational, and it's down here at the bottom, internal flow distribution, there's my internal recycle. So I have specified that one, I've checked that one off. And then the other one is the anoxic fraction, which is actually found here in the physical menu. And if I go to volume fractions, we can find that right here. So this is checked off. And just to let you know, in the background, I've actually thrown in one other equation so that the volume fractions will add up to 100%. So no matter what this is set to, I've set the other one to 100% minus that value. So that way the optimizer can move that around independently and not have to worry about it adding up to 100%. Okay, so then the next step, I'm going to leave all of these at the default. We're doing a minimization of our target variable, effluent total nitrogen, and then I hit finish. And then it takes us over. When you do this the first time, it will go through a build step here, and then we're all set. So we've got our parameters up here. We're looking at our optimization results. This is the thing that we want to run, and it's already set up for us with the optimizer turned on. Now, before I do it, though, I'm going to turn it off just for one moment here and actually run a simulation. So this will tell us where we're starting from. Right now, the effluent total nitrogen is 14.37 milligrams per liter. So that's saying that under the current settings that we have, the effluent total nitrogen 14.4. So keep that in your mind. I'll turn this on, and then I'm going to hit start. And you'll be able to see the successive guesses of the optimizer over here, and then you'll see the numbers that it's trying out up here, and these will eventually converge. So yeah, that's on. I'm letting this run now, and so hopefully you can see this well. There's lines being drawn here, and you can see they successfully get lower and lower and lower as the optimizer is adjusting these values up here. Now you can actually set the bounds of what you want these parameters to be bound within here. I'm letting it go up to 6,000 meters cubed per day in terms of the mixed liquor, and I'm allowing it to go up to 100% anoxic if it felt that was what it wanted to do. And we can see here now it's pretty much getting to the point where it's converging. So most of the successive guesses here, as we can see, are pretty much drawing right on top of each other. And it's going to converge and stop here in a moment and get us essentially to the best answer that it possibly could have done. And we can see here these numbers are pretty much converged now. We're showing, approximately 25% of that tank is the anoxic zone up front. And here it's pretty much maxed out the internal mixed liquor recycle as far as I would let it go up here at around 6,000 meters cubed per day, which by the way is 3Q. That's where I picked that number from. Okay, so this will take a little moment here. I think I've probably got this termination criteria set really tightly here, but we can at this point take a look at the effluent quality here, the composite variables, and we can take a look at total nitrogen. We can see here it's around 8.2, so it stopped now, and this is the value that it got at the end. So we started out with 14.4, and then it optimized those two variables to get to 8.2. So I have a slide that actually summarizes that nicely here. And we started out, as I said, at 14.4, and it made the changes from these initial values that we gave it to these initial values here and got us down to 8.2. Now, it's not taking anything else into account at this point. It's only solely focused on reducing one parameter to the lowest value that it possibly can. All right, so now let's try and look at something a little more challenging. So this one will actually be a 4-parameter optimization, and it will be done trying to minimize total energy cost. And we're going to do that by making some adjustments to the pumping rates of various pumps in the plant and also the amount of air that's being used. All right, so I'm going to close this one up. And I'm going to go to my second demo here. And I'm going to pop back and quickly show you how that was set up again. So we'll click here, bring that menu over. And in this particular case, our target variables are total energy cost. So in this case, that's found in the system menu under operating cost. And if I look here at total energy cost, you can see that that's now been checked off. And that is the only target variable that we are using. You can actually display that from this little pull-down menu here. All right, and then the next thing that we're doing is the optimized variables. And actually there are 4 of them in this case. I picked all the ones that are actually using energy. So in the primary clarifier, we can take a look under the operational menu, and we can see here that I've checked off the underflow rate. Then in the aeration tank, we've also done the same thing here where we have airflow. And then for the, oops, I gotta close that one up. And then for the secondary clarifier, we're looking at both the RAS flow rate and the wastage flow rate. So 3 pumps and 1 aeration. So that allows us to basically have control over all of the things that are using energy in this simple hypothetical example that we're doing here right now. Okay, so, and again, minimizing. We're minimizing, in this case, not effluent total nitrogen, but our target variable here is that energy cost. So let's finish that up. And we can see here total energy cost on that axis. And I'm going to, one more time, do the same thing. I'll turn this off. We'll run it once to see where we're at. $427 per day to run this particular plant. in terms of the energy that is used in those 4 particular places. So there's our 4 things that we're going to optimize. I'll turn that optimizer back on, and then we'll let that start. And we can see that it's taking a number of guesses and very quickly moving that value down and down and down. So as you can imagine, this is an optimization that is saying the only thing I want to do is to minimize the amount of energy usage in this plant. So what has it done? It has, of course, just turned everything off. That's what happens when you have an unconstrained optimization here. It doesn't have anything else to tell it to do other than just reduce energy. So the only thing it can see is the way to reduce energy. It doesn't care about anything else. So right now, it basically reduced our cost to 0 by turning all these things down to 0 pretty much. Okay, so what does that mean? We need a way to make it so that it's more realistic, like that what you would have in a plant. So of course, you wouldn't turn everything off. You're going to be also bound by the quality of your effluent. So we have input a new feature here in our effluent model. If you look here under input parameters and you look in this thing called the effluent quality index, it allows us to basically specify some limits here for these particular concentrations that are coming out of your plant. And I've left all of these at the default, but they're there to sort of specify limits that you would like to achieve in this given effluent. And then what it calculates is this index down here called EQI, Effluent Quality Index, that is a sum, a weighted sum of all of those different things that are flowing out the back end of your plant. Now, if it's meeting all of those limits, the net EQI is 0. It's only going to start becoming greater than 0 when you are not meeting those limits. So this becomes a very useful tool to also minimize alongside our energy usage. So what I'm going to do is I'm going to go back and add this to our optimization. So simultaneously, we will be reducing the energy cost, and we will also be reducing the EQI. So in other words, we want that to be balanced together. So the way I do that is back into this menu one more time, and I'm going to, in addition to the target variable that's already been specified, I'm going to go to that effluent object. I'm going to go to that effluent assessment criteria, and I'm going to take that net EQI number. So we'll check that off, leave everything else the same. So now it's going to be reducing both of those things. So of course, as it reduces the the energy uses, it starts to try and turn things off again. At some point, that EQI value will certainly not be 0 anymore. It'll jump way up, and then it has to do that balancing back and forth. Okay, so remember that we were standing at $427 a day before. So this is now turned on. Everything's ready to go. And we're going to go ahead with our energy cost. Let me blow that up for you. So you can see now it doesn't push it all the way down to 0. It dropped a ways, but then now it's at that point where it was starting to impact the quality of the effluent, and that EQI number is also coming into the mix here as well. So, oops, I should be plotting that. Pardon me, that should be plotted here on a much better scale than what I've got. There we go. So we can see the EQI number there as well. So now this optimization is doing its job. It's saying I'm going to reduce the energy as much as I can until it has a big impact on my effluent quality. So now it's actually converged to a completely different set of answers, and it's got this down about as low as it possibly can go. Okay, so now that's more like what you would normally have. And the difference between this and what we did before was we included effluent quality into the optimization. So we can see here now we've got an underflow rate, and we've got a certain amount of air. It's been dialed down from previously, and we also now have got our airflow, our total energy cost down from 427 to 290 something. In fact, I've got all of those numbers nicely on a slide right here. So this is where we started out with our $427 per day of energy cost. And while we were keeping that EQI constraint, that effluent quality constraint in there, it now reduced it down to $294 per day. By making these changes, it dropped the primary wastage, it dropped the airflow, it put the RAS up a little bit, also changed the wastage a little bit, and so on. So it's now making those changes as it wants to by doing that numerical optimization. So if I look at the effluent quality here, those are the targets that I was showing you earlier. It's really interesting to take a note here. This is where we started. We were meeting most of those effluent qualities, not total nitrogen, but everything else was met pretty well. In fact, we were quite a bit lower on many of them. But when we ran the optimization, note that it basically matched up with the ammonia, TKN, and total nitrogen numbers. So what this is telling us is that optimizer dialed back the aeration and it made adjustments in order to basically back the treatment off as far as it possibly could until it reached that point when it hit that limit. So basically the ammonia, part of that nitrogen side is what's really driving this optimization here. And I played around with this quite a bit this week. If you go in and you change what these limits are, it actually changes the way that it does the optimization, you know. So the interesting thing is here, it's basically dialing back the aeration, but it's also at the same time making the SRT a little longer and carrying a little more solids with it as well. So it's a very interesting thing to be able to play around with and understand what is the globally best possible set of parameters that we could use in order to achieve a certain objective. And in the end, we did reduce it down quite a bit. Okay, so that's our process optimization ones, and I will end here with a parameter estimation example. So fundamentally, it's really the same thing going on in the background here, except what you're doing is you're extracting out input values by trying to match to model data. So you're not minimizing or maximizing a number, but you're trying to minimize the difference between a simulated value and some measured data points that you fed into GPSX. And you do that by selecting that from this target comparison menu here, and you can even use that button to add your data file right now. So it looks like this. Basically, we'll set it up, and we want to know which parameter values will cause the model to give the best fit to this particular data. I will mention, by the way, that we do also have a statistical evaluation that gets spit out at the end, if you like it, that talks about the statistical goodness of fit measurements too. So what I'm showing you now is actually going to be tutorial 8, so you can go through and do that yourself, or you can watch our tutorial videos online to see how that works. So let's just jump back here one more time. Go to tutorial 8. And we can see here what we are looking at is a batch reactor. So in this particular case, we have a batch reactor. It's aerated. It has a given amount of substrate in it at the beginning of the simulation. And when I run this, I won't turn the optimizer on yet. If I just run it once, we can see these are the measurements that were theoretically taken in this experiment that for this readily biodegradable substrate that's been left over in that tank. And we can see that, of course, as time goes on, that the biomass is using up that substrate. And here's the parameters that we're trying to fit to are the specific growth rate and the half saturation coefficient for the substrate. And so right now we can see that these two values do not give us a very good fit for the data that is showing. So let's turn on the optimizer. And I'm going to actually put a little bit of a delay in running the simulation, because otherwise it'll go by so fast you won't be able to see it. So what you can see here, hopefully, is successive runs, and it starts out with wide swings on either side of the data, but it then converges down right onto that data set that we have there, and it fits to statistically the best parameter set that you can have. So this is very useful for things if you have like respirometry data or any other sort of OUR type test where you have data, lab scale data that you would like to be able to use. You can start out by fitting that data and finding some of these parameters, these kinetic parameters that you wouldn't otherwise be able to easily, readily identify in maybe another different context, and then put those together and then run your simulation and get some data out. Okay, so that gives us our minimization, maximization, our process type optimizations, and then this is doing parameter estimation, which is not trying to change your design of your plant, but rather back out some of those biological parameters from a given experiment that you might have. All right, so let's move on to those tips and pitfalls, things that you need to think about when you're putting together an optimization. is that the optimizer is, I put quotes here, is blind to anything that you don't put into the objective function. In other words, it is only going to care about the things that you've specified in the objective function. So, for example, I showed you earlier that we said, I want you to minimize total energy, and it did. It just basically turned everything right off because it didn't know that it was supposed to also care about effluent quality too. So once we put that in, then it started to work. You can also set bounds, as I mentioned before, so that the parameters that are being adjusted by GPSX don't go into ranges that you don't like. And basically, it's the same thing. If you open up the properties menu where the sliders are and where your optimized variables are, and you just set the minimum and maximum as you would normally. And I've been showing you almost completely steady state here, except for that last parameter estimation bit. But this really can be used both for steady state or for dynamic runs too. And this is an example from a project that we did many years ago on a wet weather event. And this is looking at BOD as the beginning of the wet weather event happened during that first hour there. And this is the way things would normally go. And then we used the optimizer to show that if you did step feeding in certain optimized routines, certain optimized distributions, I guess you could say, that things would get better, and that we were letting it run over and over and over again to try and find the best settings for that minimization of that BOD that was going out through the plant. And another thing to keep in mind is that the optimizer will literally take every inch that you give it, so to speak. It will continue to move a parameter until it has no reason to do so anymore. And I noticed that the most this week when I was putting this together by playing around with the RAS rate, the recycle rate. I noticed that in many cases I was playing around, say, with that effluent total nitrogen number, and I had a very large maximum value. I didn't really care how high it went up, and it would just go as far as it wanted to. Like it would go up to 5, 6, 7, 8 Q. And really, it was only gaining like an extra 0.1 or 0.05 milligrams per liter of total nitrogen. But because that's the objective of an optimizer, is that it's going to take that time. So even though you've really reached the point of diminishing returns in terms of the betterment that you get by going up to those higher and higher RAS rates, that's what it does, because that's the way the optimizer works. So the point is, it's often worthwhile to set your targets a little bit conservatively in order to account for that. So if you are including that effluent quality in your system, you may want to put it at a little bit lower than what you would normally identify with, because it's going to take every opportunity to get as far as it possibly can. And you'll notice too, if you play around with optimizing airflow, that it will likely favor a very low airflow rate, a very low dissolved oxygen, and really try to optimize simultaneous nitrification, denitrification if you're getting into areas where you're trying to optimize nitrogen removal. And the way that you can deal with that, you may end up with only 0.4 milligrams of DO or something like that, unless that's really the type of optimization that you're looking for. It may be a little lower than you're comfortable with. There may be many other reasons, mixing or bulking, that you don't want to go down that low. And the way to do that is just make sure that you have applied appropriate bounds on your system so that you don't let it go any lower than that. So the simplex method, it really follows a path from that initial guess that you've given to what it thinks is the globally best answer. Excuse me one moment. And so it's worthwhile trying a number of different initial guesses. And by that I mean the initial settings that you've built into the model for the parameters that you're allowing it to optimize. Starting out from different places can sometimes get you to a different optimal answer. And lastly, take advantage of those things like the energy cost and the effluent quality index to keep it honest, to keep it so that it's in that range of appropriate wastewater treatment design, so that it doesn't try to sacrifice one thing in order to optimize something else any more than you really want it to. So sometimes you have to keep those in, or otherwise you'll come up with a trivial answer. So in conclusion, GPSX Optimizer is really a very powerful search routine, and it's really interesting to actually use and play around with. It really is excellent when you want to use for optimizing a design where you're allowing it to change clarifier surface areas and other things, RAS rates and wastage rates and so on. Or you can even turn on controllers and then let the optimizer have control of the set point. All of that kind of stuff is really kind of fascinating and very advanced types of analysis. And then what it can often do is sort of illuminate other ideas or other operational spaces or regions that you maybe hadn't thought of by saying, you know, really if you were to run at a much lower SRT, you may find that it does this or that or whatever. So it's worth playing around with if you have the opportunity.